One of the things I asked is if people could just say hello and put your name in the chat, where you're from, what you're hoping to get out of this series. And welcome, everyone. Really great to have you all here. My name is Sally Phelps, and I'm the Director of External Programs and Partnerships. And I work with our alumni to help them share what they've learned through these Olin Learning Labs. We actually are recording tonight's session. I just wanted to let everybody know. Last June, we graduated our 18th class, and we now number almost 1,400 alumni. That's a big number for us. At a growing rate, these seniors have grown into alumni working in fields where they can truly have impact on the substantial global challenges we're facing. They're working on the hard problems, and they're finding solutions. This is the second segment of our latest learning lab, featuring alumni working in energy systems, software careers, storage, and wind. Tonight, Emily Guthrie and Ert McMullen will talk about the energy challenges of microgrids and fusion and how they take an innovative systems approach to solving them. Emily, 16, is an electrical engineer who's worked across industries from wireless communicator modules, IoT sensors, and as of recently, energy systems. Emily enjoys the full product development cycle from definition to deployment. Ert, class of 13, is a mechanical engineer whose background involves aerospace, structures, mechanisms, actuators, and most recently, ultra-high vacuum and ultra-high voltage systems. Ert has the most fun when he's turning crazy ideas into prototypes. Sounds very Olin. Ert, I'm going to let you get started. Love for you to take it away. Welcome.
Start by unmuting. Hello, everybody. I am Ert McMullen, class of 2013. Let me share this here. I have some pictures. Okay, yeah, so I'm talking about the company I work for and my role here, Avalanche Energy. So Avalanche Energy is a nuclear fusion startup, and we are working on clean, compact fusion energy. Really, really, really compact. When we say compact, we're talking like this big, like human scale, I like to call it. So I'll get a little bit more into that and how in a second here. So about me, I'm a farm boy from Minnesota, went to Olin, graduated 2013, mechanical engineering, and Sally probably gave a better summary of my career than this, but originally went to oil and gas, then quickly got out of there, worked for Blue Origin for about 6 years, first mode for a year and a half, and then landed here at Avalanche. And I've been here for almost 2 years, or a little over 2 years, actually. So I am the mechanical engineering lead, mechanical engineering lead here, and I basically have been here since the company started. So it's been a really fascinating and interesting and usually fun, but not always experience is starting from basically day one as a startup. Currently, we have 2 Olin alums at the company, and we're planning on more. And for all the current students out there, we have some seriously legit internships. We basically just throw the interns in the deep end and give them actual things that matter to work on day one. And our company takes a pretty similar approach to that you learn at Olin. We're trying to do something that's never been done before, and we're solving problems that have never been solved. So by necessity, we are doing spiral learning. And there's a lot of cross-functional teamwork. It's a lot of hands-on stuff. And I'll be at the career fair on Wednesday, so come say hi. So about Avalanche, currently we have about 30 employees. We've got a relatively large chunk of PhDs and scientists. And then we have sort of the engineering side of things. So the way I like to describe it is scientists come up with really, really crazy ideas, and then the engineering team figures out how the heck we're going to build that and make it so that we can test it. We're in Seattle. That's a basically we got our funding starting out in summer 2021, so a little bit over 2 years ago. And we've been actively doing fusion for a year and a half now. So that's pretty exciting. We still have a long way to go, but getting first fusion was definitely a pretty insane moment, because we thought it was crazy. So real quick, for those who aren't experts in nuclear energy, there's fission and there's fusion. So fission is what nuclear power plants today use. You take a big heavy isotope, usually uranium or plutonium, break it apart, it releases energy, and you get these byproducts that are radioactive and last a really long time. So those are kind of a problem because you got to deal with them. And then also it's really easy for this to happen. So you have the possibility of a meltdown, which is like Chernobyl, Fukushima, bad news. And then also it's pretty easy to make nuclear weapons out of this stuff, which is bad. So fusion is sort of the opposite of fission, although it's similar in other ways. But instead of splitting apart a heavy thing, you're fusing together two lighter things. So usually those are hydrogen, although there are other things you can do, and usually you end up making helium. So usually your products and a lot of times your inputs are not radioactive, or if they are, they're very short-lived. So there isn't a nuclear waste issue. The amount of energy you get out per reaction is more than fission. So in theory, you can create more energy for the same amount of fuel, and you can't easily make nuclear weapons out of it, and it can't go supercritical and have a meltdown like fission. Generally, good way to think about it is fusion is really, really, really hard to make happen. That's why we still don't have commercial fusion power. So it's not going to accidentally go on its own. But of course, the problem is these two atoms really don't want to fuse because they repel each other, and you need a ton of energy to get them to do that. The sun is the most successful fusion reactor that people are familiar with, and it has the gravity of its enormous mass to make it happen. So actually getting this to happen is really challenging. People have been trying for the last 70 years with varying levels of success, but not lots of it. So we're continuing the push to make it happen. The payoff will be huge if it does happen, because it's basically it's carbon-free energy. The fuel is abundant. It's basically seawater, and it's, you can generate almost limitless power with it. You don't need the sun to be shining. You don't need it to be windy that day. It just always works. So what are we actually doing at Avalanche? So we're trying to make a microfusion reactor, partly because it's really useful to have a very small one, and partly because that's how our method of doing fusion works best, is small. So what we're doing is called electrostatic fusion. So we are basically using high electric fields to accelerate the fusion fuel ions, so that they smash into each other really hard, and that causes fusion. So if you look at this bottom image here, our device is based off an orbit trap, which, without going too far into the details, it traps ions in orbits around a central cathode. And so basically we're doing that with fusile ions at really, really high energies, so that when they do collide, they fuse. And then basically we put enough in there that the fusion rate outweighs the amount of energy we have to put in to keep them there. And then we get energy out. That's the theory. And just this is sort of the scale of a theoretical finished final product prototype. We're definitely not at this stage yet, unfortunately. This is just a fun little animation showing kind of how these ions orbit. So you can see on the left, that's looking down axially, so you can see how they're orbiting, and then on the right, you can see how they're axially sort of oscillating back and forth. And basically, that's sort of it in a nutshell. It's a lot less simple than this in practice, but the general concept is you do this with enough ions, and that's how you get fusion. And I'll say that we are actually testing. Whoops, I don't know why it won't play the video again. We're actually doing this testing. We're like today, literally today, we were running tests where we were doing this. And there's a lot of nuances to get out. And so, you know, every test, really the aim is learning. We're definitely not making power yet. We're doing relatively low density, so we don't have enough ions to produce net power yet, but the goal is to get there eventually. So to sort of bring it back into sustainability, so why fusion? So there's a lot of work going into decarbonizing the power grid, which is sort of furthest on the right over here. That's like replacing coal power plants with solar power and wind, which that's the biggest polluter. So it's the right place to start. And then there's also a fair bit of work being done on things like electric vehicles, sort of the smaller side of it. But there's sort of a pretty big gap in between for things like shipping and airplanes and long distance trucking, all that kind of thing, where batteries aren't a good option because they don't have enough total power storage yet. Hopefully they get better too. But like you can't use a solar panel to power your truck because it's got to run at night, stuff like that. So there's a lot of mobility applications that require medium power output. And that's kind of our goal with this fusion reactor, is that it can fill that middle ground. Hopefully it could probably work for both ends also, but a lot of the current work in renewable energy sort of misses this middle chunk. There is plenty of work being done. There's some fun work with hydrogen, which I was doing at my last job, first mode. That's super cool. But if there were a compact fusion reactor, it would be way easier than all that, because that's kind of a pain to deal with. There's a lot of energy going from chemical to electrical to mechanical. There's a lot of energy conversions, and all of them are inefficient in that. That's sort of the niche that our reactor probably fits in, hopefully. Obviously it has to work first, so that's obviously the big caveat on everything. But the goal is to be able to target that middle ground. Just a little bit more about so there's a lot of fusion companies out there. The biggest difference is that ours is so small that we're really able to rapidly iterate, and that's why I like the job. That's why it feels a lot more like Olin to me than like a huge like ITER size power plant, which is a huge one they're building in France for the last 20 years. So we're every week we'll have a new idea or a change we want to make, and usually within a week or two we'll implement that change and try it. So we're iterating really fast. We can build a whole new reactor in the matter of like a month or two, instead of a civil engineering construction project where you have to start by digging a hole in the ground that takes years to decades. That's also probably our competitive advantage. If we have one, it's that we get to try a lot of things really fast. We can get it wrong a lot of times, and that's okay. So this is what our actual test kind of looks like right now. For all the hardware lovers out there. So this center bit is where the actual Orbitron reactor is. You obviously can't see it very well. That's why mostly I show diagrams, but it's in there. And then up here, we've got our high voltage feed through. So one of the big challenges with this reactor is it needs to run in the hundreds of thousands of volts, which is difficult to work with. And so a lot of what we spend our time doing, especially on the mechanical engineering team, is figuring out how to get high voltage from a power supply to that central cathode of the reactor to make it work, which I probably failed to mention earlier. But this central cathode is at a really high negative voltage, like hundreds of thousands of volts, and that's what makes these positive ions orbit. So that's one of the big engineering challenges, is the really high voltages involved and putting them in such a small place. And then this over here is our ion gun, which generates the ions that get captured in these orbits to fuse. So we're taking a neutral gas, ionizing it, accelerating it, focusing and steering it, and getting it into there, capturing an orbit. Then we have a lot of diagnostics to try and figure out what the heck's going on in there, because you shoot in a bunch of ions, and how do you know if it's fusing? How do you know if it's fusing the way you want it to? Things like that. So that's what this kind of thing is. We're looking at neutrons. We're looking at what energy they are. We're looking at X-rays. We're looking at various voltages going to different places, currents going different places. I could talk for an hour about them, but I won't. And this is just sort of what our facility looks like. So we've got one fusion reactor in here, another one up here, and then we have some test areas for testing out components sort of scattered around. And this is just some action shots. This is a good one for when we get to questions. I'm not going to bore you with the this progress slide, but basically, really, we have 3 goals right now, and one is to really understand what our reactor's doing so that we can match it to our simulations. And then the other ones are to increase our voltages and magnetic fields so that we can do a more dense fusion and get more energy out. And that is exactly what this chart's showing too. Basically, this is showing the voltages we need to get to. And we're kind of right here. We're going this way. Anyway, that is it. I'll go back to this one because it's cool looking. But actually, I guess we're gonna do the other presentation and then do group questions.
That's what I was thinking, if that's okay.
Works for me.
We'll let people just think about their questions, and Emily, you're ready to take it away?
I'm actually having a quick technical difficulty with sending my slides through to this computer, but if we want to take questions on the original presentation, and then I'll jump in like 5.
That sounds great.
Thanks.
I invite people to either raise their hand or put a question in the chat, and I'm going to start. You have a scope project this year. Can you tell us about it? Yes,
we do. Yeah, in fact, I think it's well represented in this Zoom room. Yeah, so we have a scope team, and they are working on I didn't even talk about that challenge because there's so many other challenges, but basically that high voltage that we plug into the reactor, right now it's being generated. I can share again and show the, let's see, down here is the button. So you can kind of see it in this picture. Oh. Can you see my mouse?
Yep.
Cool. So it's being generated by these power supplies down here, which are like 6 feet tall and huge. And then we have to run the electricity over to the reactor through high voltage cabling. So we're doing that for up to 300,000 volts, but at higher voltages, that's going to be pretty impractical. So we would like to generate that ultra high voltage basically in the vacuum chamber right next to the cathode, so that we don't have to transmit it. So that is what project they're working on, generating ultra high voltage in a vacuum in a compact way too.
Awesome. Thank you. Julia has a question in the chat. She said, I heard the fusion input is basically seawater. What's the required filtration purity of the input?
Yeah, so when I said seawater, I meant the elements are readily available in seawater. So really the inputs are mostly hydrogen in various isotopes. And there are different ways of making fusion, but the one we're doing right now is deuterium fusion. So seawater is like 0.01% deuterium. And deuterium is just an isotope of hydrogen with a neutron. So you have to purify the water and then separate the heavy water from the regular water, and then you have to split the hydrogen off of that, and then concentrate that deuterium. I don't actually know the order they do it. I know that right now I buy a bottle online and it comes full of like 2000 psi deuterium, and it's not even that expensive.
Thank you. Other questions for Ert? Emily, how you doing? You ready to take it away?
I have a question, maybe.
Sure.
This might just be me not totally understanding the graph that you showed, but would you say that you have done fusion and you just need to like do more fusion, or like have a better ratio of inputs to outputs? Like, I feel like my mental model is that people haven't done fusion really yet. So I didn't know how to ask the question. I'm like, did you do fusion? I don't know. Is fusion happening?
Yes. Yeah, no, it's a good question. Yeah, it turns out fusion isn't actually that hard to do. That's like a dirty secret. Like you could build you could build a fuser in your garage, and do fusion. So yeah, it's really about densifying. So like right now we're like in this range of densities, and to get to our power producing one, we need to be up at like this densities to get more power out than we put in. At lower densities, yeah, at lower densities, you can't get more power out than you put in. So it's a little bit more in depth than that. It's the triple product, but yeah, it's basically how long can you confine the ions for, how many ions can you have, and how high of energy can you have those ions, and all those things increase the amount of fusion you get. And then when that number is high enough, you'll get more out than you put in. And that's like from a purely from a nuclear plasma physics sense. That doesn't count things like how are you getting your vacuum and how are you cooling things?
Right.
So like whenever, like if you read in the news about a successful fusion experiment and they list like a Q number, which is a Q ratio, which is the energy out over the energy in. Like a few months ago, there was the big thing about doing that in that place in California, Lawrence Livermore,
Yeah.
where their Q was like 1.3 or something. That's the Q plasma, not the Q
Lasers.
real engineering world.
Right.
Like you couldn't plug itself into itself and have it run. So yeah, this is all theoretical and the plasma Q, and then you actually have to have an efficient system as well, which honestly not a lot of work is going into that problem yet, because if you can't do the first one, then you have no hope of doing the second one.
Right.
Yep. Good question.
I have a quick question. Erd, how much, since you've been there for like a really long time in the company's lifetime, how much of your work now is like managerial versus technical?
Yeah, it's a good question. It's pretty good ratio still. Well, with my interpretation of good, it's probably 80-20 technical to managerial. But yeah, I have a team of mechanical engineers and machinists that work for me, or work in my group, I'd rather say. And yeah, they're all awesome. So I don't have to spend much time managing them.
Cool, that sounds awesome. Thanks. And yeah, just obviously wanted to say what you're doing is super, super cool.
Thanks.
Good job, Bert. You ready for us, Emily? Awesome. So when I first heard about this company, Hala Tech, I got really excited. Emily, I don't know if they still have that video on the website, on the homepage, that shows what happens when the power goes out everywhere else. Hala keeps things moving. And when I heard you went to work there, I was so happy. So take it away and tell us what you're up to. What's going on at Hala Tech?
Yeah, absolutely. Hi, everyone. I'm Emily Guthrie. I am one of the staff hardware engineers at Hala. And I am excited to talk to you all about the decentralized control and optimization of DERs, which stands for distributed energy resources, which is kind of the bread and butter of what Hala's technology, which is a microgrid controller, operates and provides to the world. And like Sally was saying, the primary focus of why we end up wanting to move down the role of implementing microgrids is in part for us to be able to decouple ourselves from the grid as we have more sources of energy that may be local to our homes, but in Hala's context of where they've focused most of their market fit is in industrial applications, where we know that the carbon impact of the energy that's consumed by those companies and those locations is fairly large, and the opportunity for leveraging renewable energy in the context of solar and battery storage and all of the sort of localized power equipment and distributed energy resources that we can have in a given site requires some complex control and some integration with the larger grid in order for us to further move towards sustainable futures, where sustainability defined in its most basic sense, we're generating power local to our location and then sustaining our businesses and operations off of those generated power pieces. I didn't include a slide about myself, so I'm just going to talk about myself on the top here. So sort of like Sally said, I recently made the change to move over to Hala. So as far as the whole institutional history, there's a lot there that I would encourage you all to reach out and come to Greentown for some of the engagements of some of my other coworkers who have the 6 years plus that Hala has existed before it was acquired by Kohler, as you can see here. My work before that was working in the space of IoT technology, so I brought a lot of wireless design and sort of integrated circuit hardware on the low scale, low power. And so making the move to Hala was not only an opportunity to move to a more mission-driven application of my skills, but also an opportunity to change the context of doing electrical engineering work from how long can you get it to last on a battery, and all of the nuances of those design optimizations, to resiliency, reliability, and working in a much more for lack of a better word, different power environment, both from a safety perspective to a stability perspective, and all of the key characteristics that we have to make in our metering systems in order for our systems to work, which I think is a good opportunity to jump into some of my slides. If I can. Yes, okay. So as I said, HALO's mission is to transform the energy industry from the ground up using DERs and microgrids as the pillar of a clean, resilient, and equitable grid. And the way that it does that is by orchestrating fleets of DERs with embodied intelligence. So one important thing to think about when you think about the technology within a microgrid is that most of us think of the controllers, or in the case of the traditional grid, the power utilities, as the only part with intelligence. It's making decisions about certain things. We as individuals consume on certain patterns, and we have intelligence. So we'll make choices about how, or some days I have intelligence, some days I don't. But in those environments, we're making choices about when we're using energy. We're trying to make choices based off of what the demand response of the grid at that time may be. And in addition to that, the utility is responsible for sort of predicting and creating models around that, as well as ensuring the stability of the load to the rest of all of our houses, knowing that it's a very different set of parameters to optimize for in the middle of the night versus when we are coming home from work and we're all flipping on our air conditioning and throwing on our lights. And so in this environment, when we stand up DERs, on board, they have their own version of intelligence, but we're also responsible for controlling and making decisions on those devices' behalves, which creates a complex ecosystem of varying levels of smart devices communicating with each other in the intent of making decisions that previously were responsibilities of the grid.
Emily, if I could jump in for a sec, I don't think your slides are advancing.
Oh, thank you for letting me know.
We still have your main slide.
Okay, thank you for letting me know.
Sure.
Shoot. Okay, well, if you guys don't mind, if I just drop here.
Yep. That works. That worked.
Great.
Good. Now you're there.
So for whatever reason, presentation mode was not working, which I think we all can relate to on PowerPoint. So this is the slide I was talking about with relative intelligences and the mission of HALA. And jumping in here, sort of as I was saying, it's a rigid and complicated system. So when we have centralized control, a single central device monitors and controls and optimizes all of the DERs for both local objectives and system level goals. So this models very closely to what our current system on the grid looks like. You can create customizations, make it rules-based, but there are single points of vulnerability in the form of that singular control source. In this context, if it were to go down, you lose all of the coordination of all of your assets, which is like unsafe. It's also critically bad for operations. And so all of these things become reasons for why we should consider different models, or at least flexible models, of how this control should work, which gets at one of HALA's core differentiating implementations in their microgrid. It also has high integration costs, and it's hard to scale or modify. We also should acknowledge that, kind of like I was alluding to before on the statement of why DERs having variable levels of intelligence, but also handling very different responsibilities, and each site dictating what it may need in terms of uses. For example, if you're talking about at a farm, you have alternate options for what like your solar capacity might look like, what storage looks like, also how far of a geographical range you may be distributing your technologies across. And so when we talk about generating a controller, there are a lot of environments that we have to imagine it for, and it's very non-standardized. And there are also fairly complex systems where we're coordinating between a lot of different pieces that have strict time dependencies, have strict requirements for the precision of what their communication and calculations need to include in order to achieve their objectives, which adds an additional complexity to the technology that underpins HALA's microgrid controller. And we also are dealing in dynamic environments. Sites and markets really change quickly, especially if HALA is to integrate effectively with the grid. We should be taking similar models and the outputs that come from the utilities that tell us about the demand response, tell us about the economic drivers, if we were to be doing buyback programs, and all of that impacts significantly how we have to adjust the algorithms and the optimization that's existing within the controller, which all of my brilliant software peers facilitate on the hardware that we design. We at HALA decided that from a centralized controller with all of those limitations that I outlined first, and given the constraints that are on that second half, we needed to move towards something even more distributed. So within an ecosystem, the grid itself is controlling each of our sort of larger response from utilities, but independently, we will have controllers and potentially even architectures that include multiple controllers within a given site that work together to be able to facilitate subparts of what the needs are of independent areas of control within the customer site as we need it. This gives us flexibility. It gives us the ability to address specific timing. It allows us to work on more complex solutions with a hierarchical coordination of these devices. And we find that that helps us to also improve our resiliency as we have more than one point of failure, and we have redundancy in the form of multiple backup controllers, which is not a novel concept, but it is something that in microgrids, we find that given the custom implementation of HALA's controller, there is quite a bit of benefit to that, and it represents one of the challenges that exists within designing a microgrid, which is why I wanted to highlight it. I would also say that each DER is made as a controllable and intelligent building block. So within our HALA program, there's quite a bit of modeling that's made around each type of resource and the types of parameters that may be customizable per parameter that allows us to integrate with a wide swath of different DR technologies underneath this singular model, which then means that we have the ability to abstract from both the technology at a manufactured level. We have an inverter from this company, we have an inverter from some other company, we can use both of them. We also have the ability to abstract communication protocol, and through these abstraction layers, I think it highlights the systems level thinking that HALA implements in their designs, which is to say, each of these layers of abstraction allows the teams to interact with each other in a way that abstracts the underpinnings of what we decide to change in the hardware interfaces, or abstracts what we need to change in the models of the core technology for a given type of DER, and allows each of us to work and innovate on the solutions that we're providing concurrently, which is one of the ways that I think teaming ties into the systems level design of a microgrid controller, and certainly in the context of HALA is how we approach that. We also know that the DER level decisions will have to drive parts of transactions. So each DER will tell the other DERs how much of each commodity it seeks to supply or take and at what price. These all are able to be coordinated through our HALA device as a core communication, understanding that each DER, given its limited intelligence, is not designed with the intent of being able to talk to everything else in the ecosystem. And so this coordination is responsible. You can think of the coordinator as sort of a language translator between respective DERs to help facilitate these interactions working effectively, as well as to provide insights of itself for information that the DER isn't prepared to factor into its modeling. And when we end up using the controller in this context, the DERs are achieving consensus, but through the HALA controller, resulting in a schedule for import and export. It also allows the power market to run on a second-by-second basis to maintain the optimal course of the energy market sector. I'll talk a little bit more about how microgrids allow us to align incentives for the financial impact, the ecological impact, and in this case, we're talking about agreement between us and the utilities about the cost and utilization for financial impacts, but there are other ways that we run additional algorithms as a part of modeling the power market to meet our customers' goals of both becoming sustainable and also the financial incentives that come from the control optimizations that we do. And then this output for the algorithms, as I was saying, allows us to create desired states for DERs and have feedback control loops that adjust as necessary as we get new information from outside, as well as when we get information from inside on the DERs, more towards the system level thinking that's involved in how a microgrid is constructed, as well as some of the technological complexities that we encounter on a daily basis when designing the technology. So this is what I was alluding to, that there are a lot of ways that DER level decisions can drive transactions, and that there are specific economic incentives according to this. So we can take a look at what the grid prices are, the grid power levels are, or in specific the demand response, and then look at the DER levels of power that are being output, and it autonomously is able to rebalance during high load and congestion for how much of the DERs are being leveraged in a given situation, how much is going into storage, versus how much is being pulled from the grid, which in this case has both financial and ecological impacts. But this specifically calls out the ways that HALA allows you to model for economics, which I'll explain why it's important to focus on economics when we talk about getting adoption of sustainable solutions like this in a few slides. It also allows us to increase our reliability. It can meet the electricity needs of end user customers when unexpected equipment failures occur. I think we think of DERs and solar and backup generators and batteries in the context a lot of reliability, especially when we think about it in the residential context, and that's 10 times fold true for an industrial context where you need the ability to have backup supplies, and that's been a core part of the design of energy systems for large scale facilities like this for some time. And when we add in the DER and control side of things, we're able to plan for an effective amount of backup while at the same time leveraging it while making those other economic trade-offs. So you're just getting more for what you've implemented in technology that already exists, which is why HALA's run down those specific opportunities because those technologies already exist on site as a part of other incentives that an industrial site might already have had. And now we add in the benefit of giving you back that financial and ecological impact. And lastly, resiliency is another part of these transaction drives. This one is for a very similar reason. It's that backup option that I already was talking about, so I won't spend too much extra time on that. And lastly, the one we're all most excited about here at this group, it helps us with this sustainability of our utilization. We can integrate intermittent renewables to help us flatten parts of the curve of the demand response of the grid, and ideally help to take some of the peak times down by being able to supply our own power in those situations, and vice versa by being able to provide back in the times where there's low response. So putting the theory to work, these are the technologies that HALA offers in this space. We have sort of three phases of technologies. The first is the HALA IQ, which allows you to do metering and assess your situation at a given industrial site. It gives you comprehensive data of models for if you were to go through and implement a microgrid, what it would allow you to do with your system. So we believe we want to educate in addition to providing the technology that will solve this. Another systems level thinking, because it represents HALA understanding that our customers need both to understand the technology and the value out of our product, and so therefore built solutions to be able to help with that facilitation. And then the edge itself, which is the control and optimization, which is where I do the lion's share of my work, given it is our core hardware technology. And then on the other side, we've got algorithms implemented as a part of the operation and maintenance of our product, as well as our service packages. The last thing I wanted to highlight as a quick trade-off analysis related to microgrid implementations that I really am proud that HALA focuses on significantly within its approach is that as we move towards building the microgrid solution for the broader world and changing the energy systems going forward with these sorts of revolutionary technologies, we believe that there needs to be an equity aspect to how we approach this, and that we think that going through the process of coordinating with DERs is an opportunity to create equity through the natural inflection points of these systems where we align incentives while inspiring engagement at the same time, by being able to pull together the economic incentives that previously have disincentivized people from making the transition over towards implementing more sustainable practices in their energy consumption or in their energy infrastructure. We're able to inspire engagement by encouraging more people to make that transition, given it is financially and fiscally responsible for their companies to do so. And in that, we see the impact of, oh, I don't know why that slide showed up again. We see the resulting impact is us seeing a more improved structure of how we consume and think about the economics of making sustainable choices in business decisions, and that is better for equity overall for all people in access to the grid, in addition to the impact of climate on all. So that is the conclusion of the trade-offs of working on the microgrid. I didn't spend too much time talking about the hardware, but I'm happy to answer questions about what my role specifically is working within that hardware. But I wanted to focus more on sort of the broader application for these slides, and thank you all for listening.
Thank you, Emily. We have another great question from Julia. What's the scale of these microgrids? Are these DERs mostly focused at the single property scale, home, farm, office, block, neighborhood, small renewable farm, city, or all of the above?
Great question. I think the only one that we haven't tackled within that list is small city. We have some residential neighborhood properties that are pretty exciting in the space of expanding towards that. There's some retirement facilities that have independent living dwellings that are all connected on their own energy infrastructure with a microgrid underpinning it. Some of our other large sites and exciting sites have been around some military bases that have very wide swings in their electrical consumption or their energy consumption, and require large scale of geographic space that we're trying to cover. On the farm side, we have a very cool winery called Stonehenge Farms that we have our microgrid testbed site at. We test all of our new product development there, and the technology there is monitoring loads with pouring wine into casks and all of the fermentation process. That's pretty cool. And the last one I will highlight is that we've recently partnered with Kohler to send a microgrid to Antarctica alongside an exploration of the polar caps down there. And so it was coordinating a generator and a solar panel for one of the explorers down there. That was pretty cool.
That's awesome. Another question from Sushmit. Who is the customer for the hardware and software product? Are they microgrid installers or utility companies?
It's a great question. I think we've played around with both. At this point in time, the majority of our clientele, though, are companies who run the facilities that are going to be converted to running off of a microgrid. So if you think about in the industrial context, a manufacturer, for example, they have people responsible for coordinating the operations and minimizing the cost of the business. And so those are typically our decision makers. And then our customer is also the microgrid installer and the operators, because they're the people who interact with the hardware on a daily basis, which creates a very interesting customer scheme where we're balancing the needs and values of people who sign the checks, who are looking to see the financial payoff of the product, but at the same time providing something that is user accessible, reliable, and sort of merges what is expected out of the new slick startup solution that is easy to use and provides interesting backhauling technology to the cloud, while at the same time meeting the expectations for resiliency and risk management that is required out of the energy sector, which is a totally different topic that I'm sure Ert and I could talk about for a long time. It's a very interesting trade-off.
Awesome. I would like to introduce, thank you, Emily, and I think we may have more questions, but I want to just say hello to one of our listeners tonight. Dylan Garrett is class of 06, and Dylan has a very cool podcast called Hardware to Save a Planet that I want to put a plug in for. He is interviewing pioneers in this space, and I learn something every single time I listen to one. So Dylan, can you say hello? I know you're kind of moving from your office to your car.
Yep.
Your phone might die.
Hey, Sally, I'm here. Can you hear me?
Yes, hear you great.
I am in the car, so I'm not going to go on video. I'm out of light, but yeah, I'm not going to do it. Anyway, this has been awesome. Yeah, thanks for setting this up. I'm like super impressed by what Ert and Emily are talking about, and super jealous. So I'm 06, and when I was going to Olin, I feel like, I mean, I'm the old guy here, but I feel like I could not. I had no idea what to do. I wanted to jump in and help with sustainability. I was a mechanical engineer. I just felt like there weren't nearly as many opportunities. So it's so cool to see what kind of community has come together in this space at Olin. And it's really impressive to see what everybody's doing. So thanks for setting this up. And yeah, check out the podcast. It's pretty fun. I'm actually, coincidentally, I'm lining up to interview one of your founders from Avalanche, actually. So it was very, very nice to get a little preview from you today. Thanks for doing that.
Dylan, I know
Nice.
you're also...
I had no idea.
Dylan, I
Yeah.
know you've also moved into the climate space with Synapse. Do you want to talk a little bit about that?
Yeah, so if people don't know Synapse, we're a product development company. We've been around for over 20 years doing hardware development for a range of industries: consumer, medical, industrial. We have about 100 engineers in Seattle and San Francisco, mechanical, electrical, software engineers, program managers. And we've always kind of just done whatever our clients paid us to do. And then a few years ago, we sat down as a leadership team and said, we have all these incredible talented engineers, what could we do to have a positive impact on the world? And we've since made a very focused effort to increase the amount of work we do that has a sustainability impact in different ways. So that has two big thrusts to it. One is we're working with companies like we heard about today that have a sustainability mission at their core. That's kind of our climate tech portfolio. And then we also help all of our existing companies. So we do a bunch of work in the consumer electronics space and elsewhere. We help them design their products to have a lesser impact on the environment through doing life cycle analyses and supply chain strategy and stuff to help them reduce the carbon footprint of their products. So that's been really cool. And yeah, the climate tech space has been fun. We're working with companies that are doing atmospheric carbon dioxide removal. We're working with companies that are doing energy generation in different ways, energy storage, waste management kind of stuff. We're building up a good portfolio of work, and it's been really fun projects. And really check out Synapse if you haven't looked into us. It's a great team.
Great. Thank you, Dylan. Appreciate you jumping in there. I'd like to turn it back over then. Any
Yeah.
other questions for Ert or Emily? Feel free to put them in the chat or raise your hand. I'd also, while you're thinking, like to call your attention, I put a link in the chat to some resources. I thank you, Tiana, for putting in a link to Dylan's podcast. I also, there's a link in there for where to sign up for the next two in this series. We will be having 3 women next from Olin who are working on wind: Erica Boeing, Meg Litterbach, and Ellie Funkhauser. Some familiar names I know to all of you. And then that will be October 11th. And then the final one will be Catherine Elliott and Aurora Bunton of Form Energy talking about battery storage. So much good work happening here. I love it. So that resources doc has some different things like that in it, as well as the recording. Earlier we had Jamie and Jason Curtis on of Option Zero. They did number 1 if you were not able to see it or hear it in this series, talking about their work helping people get careers in software in climate. So that recording is also available. Anybody else? Huge thank you to Emily and Ert for sharing your thoughts and your work tonight. This is amazing. I always feel so proud of you all.
Huge thanks to Sally for inviting us. I'm really appreciative of the opportunity to talk tonight with
Good
all of
stuff.
you. And, thanks.
Really, really good stuff.
Yeah,
All
thanks.
right. Well, thanks everyone. Appreciate your coming. Have a great night. Emily, nice job.
Thank you.